Conductor identification is crucial in electrical systems. You can use black, red, and blue conductors for the 120 volts hot leads, and grey and white for the neutrals, regardless of which leg the 120 volts circuits are tied to. This is acceptable for identification purposes within a project as long as it is consistent throughout the installation. For alternating current interrupting capacity or AIC ratings to determine the AIC rating required for the main disconnect and service panel, you will need to obtain the available short circuit current, often abbreviated as ISC, from the utility company. You can request this information from the local utility. The letters such as BR, CH, etc. for load center types are manufacturer-specific type letters that indicate different features or series of load centers. They do not follow an industry or document standard. You can refer to the manufacturer's literature or website for specific information about each type. Article 310.12 of the 2020 National Electrical Code, or NEC, allows the use of any color conductor except green, bare, or white for the identification of ungrounded conductors. For three-phase systems, it is typical to identify the phases as A, B, and C, with corresponding phase colors of black, red, and blue, respectively. If you are unable to obtain the short circuit current from the utility company, you may need to perform a short circuit current study to calculate the value yourself. This may require the use of specialized software or assistance from an electrical engineer. Let's delve deeper into these concepts, starting with conductor identification. The NEC provides guidelines for conductor identification to ensure safety and ease of maintenance. While the specific colors mentioned, black, red, blue for hots and white and grey for neutrals, are commonly used and accepted, it's important to understand the underlying principle, which is consistent and clear identification. Within a single project, maintaining consistency is key. This means, if you choose to use black for phase A, red for phase B, and blue for phase C, stick to that convention throughout the entire installation. This minimizes confusion and reduces the risk of errors during troubleshooting or future modifications. Now, let's move on to alternating current interrupting capacity, or AIC ratings. The AIC rating of a circuit breaker or disconnect switch indicates the maximum short circuit current that the device can safely interrupt without failing. Exceeding this rating can lead to catastrophic equipment failure, posing a significant safety hazard. To determine the appropriate AIC rating for your main disconnect and service panel, you need to know the available short circuit current, or ISC, at the service entrance. The most reliable source for this information is your local utility company. They typically have this data readily available and can provide it upon request. They may also be able to provide you with the X/R ratio, which is used to calculate the peak asymmetrical fault current. Now, what if you are unable to obtain the short circuit current information from the utility? In such cases, you'll need to perform a short circuit study. This involves calculating the short circuit current based on the impedance of the power source, conductors, and other components in the circuit. Short circuit studies can be complex and often require specialized software such as SKM Power Tools, Easy Power, or ETAP. These software packages allow you to model the electrical system and simulate fault conditions to determine the available short circuit current at various points. Alternatively, you can engage an electrical engineer who specializes in power system studies to perform the calculations for you. This is often the preferred approach for larger or more complex projects. When performing a short circuit study, it's essential to consider all relevant factors, including the utility source impedance, transformer impedance, conductor impedance, and motor contributions. Motor contributions refer to the additional current that motors can supply during a short circuit condition. Failing to account for these factors can lead to inaccurate results and potentially unsafe equipment selection. Next, we'll address the different load center types. Load centers, also known as panel boards, are enclosures that house circuit breakers or fuses to protect electrical circuits. They come in various sizes, configurations, and with different features. As mentioned earlier, the letters BR, CH, etc. are manufacturer-specific designations that indicate different product lines or features. For example, A BR-type load center from Kotlahama might have different features or construction compared to a CH-type load center. To understand the specific differences between these types, you should consult the manufacturer's documentation or website. These resources will provide detailed information about the features, ratings, and applications of each load center type. When selecting a load center, consider factors such as the number of circuits required, the amperage rating of the main breaker, the available space, and any specific features needed, such as surge protection or ground fault protection. Also, consider the environment where the load center will be installed. For example, if the load center will be installed in a damp or corrosive environment, you should choose a NEMA 4X rated enclosure. NEMA ratings indicate the level of protection provided by an enclosure against environmental factors such as water, dust, and corrosion. Let's look at some common load center features. Firstly, the number of circuits. Determine how many branch circuits you need to accommodate in the load center. Choose a load center with enough spaces for your current and future needs. Secondly, the main breaker rating. The main breaker protects the entire load center from overcurrents. Ensure that the main breaker rating is appropriate for the service entrance size and the overall load. Thirdly, the busbar rating. The busbar is the conductive component inside the load center that distributes power to the circuit breakers. Choose a load center with a busbar rating that is sufficient for the total load. Fourthly, the enclosure type. Select an enclosure that is appropriate for the environment. NEMA 1 enclosures are suitable for indoor use, while NEMA 3R or NEMA 4X enclosures are suitable for outdoor or wet locations. Fifthly, the mounting type. Load centers can be surface mounted or flush mounted. Choose a mounting type that is appropriate for the installation location. Sixthly, the features. Some load centers come with additional features such as surge protection, ground fault protection, or arc fault protection. Consider whether these features are needed for your application. Now, some additional considerations for conductor identification. In addition to the NEC guidelines, it's also important to follow any local codes or regulations that may apply. Some jurisdictions may have specific requirements for conductor color coding. Always consult with the local electrical inspector to ensure compliance. Consider labeling the conductors at each termination point to further enhance identification. Wire markers or labels can be used to clearly identify the circuit number, phase, and function of each conductor. For AIC ratings, it's crucial to select circuit breakers and disconnect switches with AIC ratings that are equal to or greater than the available short circuit current at the point of installation. Using devices with inadequate AIC ratings can result in equipment failure and pose a serious safety hazard. Over-designing the AIC rating can increase costs, but it's always better to err on the side of safety. Also, be aware that the available short circuit current can change over time due to modifications to the electrical system or changes in the utility source impedance. It's a good practice to periodically review the short circuit study and update the AIC ratings of the equipment as needed. Regarding load centers, consider the future needs of the building when selecting a load center. Choose a load center with enough spare capacity to accommodate future expansion or modifications. This will save time and money in the long run. Ensure that the load center is properly grounded and bonded to the building's grounding electrode system. Proper grounding and bonding are essential for safety and to prevent electrical shock hazards. When installing a load center, follow the manufacturer's instructions carefully. Improper installation can void the warranty and create safety hazards. Firstly, turn off the power to the circuit before working on the load center. Secondly, inspect the load center for any signs of damage. Thirdly, install the load center according to the manufacturer's instructions. Fourthly, connect the grounding and bonding conductors. Fifthly, install the circuit breakers. Sixthly, wire the branch circuits to the circuit breakers. Seventhly, test the circuits to ensure that they are working properly. Remember that electrical work can be dangerous, and it's always best to consult with a qualified electrician if you have any questions or concerns. Let's discuss some advanced topics related to electrical design. Firstly, harmonic distortion. Harmonic distortion is a phenomenon that occurs when nonlinear loads, such as electronic devices, inject harmonic currents into the electrical system. These harmonic currents can cause a variety of problems, including overheating of transformers and conductors, malfunctioning of sensitive equipment, and increased energy losses. To mitigate harmonic distortion, you can use harmonic filters or install harmonic mitigating transformers. Secondly, power quality. Power quality refers to the characteristics of the electrical power that is delivered to a load. Poor power quality can result in equipment malfunctions, reduced equipment life, and increased energy costs. To improve power quality, you can use power factor correction capacitors, surge suppressors, and voltage regulators. Thirdly, energy efficiency. Energy efficiency is the practice of using less energy to perform the same task. Improving energy efficiency can reduce energy costs and environmental impact. To improve energy efficiency, you can use energy-efficient lighting appliances and HVAC systems. Conduct regular energy audits to identify areas where energy can be saved. Fourthly, renewable energy. Renewable energy is energy that comes from sources that are naturally replenished, such as sunlight, wind, and water. Using renewable energy can reduce reliance on fossil fuels and environmental impact. Common renewable energy technologies include solar panels, wind turbines, and hydroelectric generators. Fifthly, smart grids. Smart grids are electrical grids that use digital technology to improve efficiency, reliability, and security. Smart grids can enable features such as automated metering, demand response, and distributed generation. Smart grid technologies include smart meters, sensors, and communication networks. Another advanced topic is arc flash hazard analysis. Arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flash can cause severe burns, injuries, and even death. To protect workers from arc flash hazards, it's important to conduct an arc flash hazard analysis. This involves calculating the incident energy and arc flash boundary for each piece of equipment in the electrical system. Based on the results of the arc flash hazard analysis, appropriate personal protective equipment, or PPE, can be selected. Also, consider implementing arc flash mitigation techniques, such as using current limiting fuses or arc flash relays. Lastly, let's talk about the importance of staying up to date with the latest electrical codes and standards. The NEC is updated every 3 years, and it's essential to stay informed about the changes. Changes to the NEC can impact the design, installation, and maintenance of electrical systems. In addition to the NEC, there are other industry standards that you should be aware of, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, the National Fire Protection Association, or NFPA, and Underwriters Laboratories, or AL. These standards provide guidance on various aspects of electrical safety and performance. Staying current with these codes and standards will ensure that you are designing and installing electrical systems that are safe, reliable, and compliant. By understanding conductor identification, AIC ratings, load center types, and staying informed about advanced topics and codes, you can excel in electrical design and contribute to safe and efficient electrical systems.